2x minus y equals 0, negative x plus 2y equals 3. You've solved systems like this 100 times. Substitution, elimination, maybe Cramer's rule. But the way you've been looking at this system is only 1/3 of the story. There are 3 completely different pictures hiding inside these 2 lines of algebra, and understanding all 3 is the key that unlocks the rest of linear algebra. Let's start with what you already know, the raw picture. Here's our system, 2x minus y equals 0, and negative x plus 2y equals 3. 2 equations, 2 unknowns. Now let's identify the ingredients. The coefficients are 2, -1, -1, and 2. The unknowns are x and y, and the right-hand sides are 0 and 3. This is the standard starting point, and equations and unknowns. Now let's see the geometry. Take the first equation, 2x minus y equals 0. Every xy pair satisfying this equation forms a line. When x is 0, y is 0. When x is 1, y is 2. Connect those points. There's our first line, passing through the origin with slope 2. Now the second equation, negative x plus 2y equals 3. When x is negative 3, y is 0. When x is negative 1, y is 1. When x is 1, y is 2. Connect those. There's our second line. Now look where they cross. Both lines pass through the point 1, 2. That's our solution. X equals 1, y equals 2. Let's verify our solution. Plug x equals 1 and y equals 2 into the first equation. 2 times 1 minus 2 equals 2 minus 2, which equals 0. Check. Now the second equation, negative 1 plus 2 times 2 equals negative 1 plus 4, which equals 3. Check. Both equations are satisfied, confirming that x equals 1, y equals 2 is indeed the correct solution. In the row picture, each equation represents a line. The solution is the point that sits on every line simultaneously. If we extend this idea to 3 dimensions, each equation would be a plane, and we look for the point where 3 planes meet. Before we see the second picture, let's write this more compactly. We can pull the coefficients into a rectangular array called a matrix. Row 1 has 2, -1. Row 2 has -1, 2. That's the coefficient matrix A. Next, we gather the unknowns into a column vector x, x on top, y on the bottom, and the right-hand sides form the vector B, 0 on top, 3 on the bottom. Now the entire system collapses into one single equation, a times x equals B. That is the matrix 2, -1, -1, 2 times the vector x, y equals the vector 0, 3. One equation instead of 2, or instead of 1,000 if the system were larger. This is the compact language of linear algebra. The matrix form is clean, but it hides something beautiful. Watch what happens when we read this equation by columns instead of by rows. Take the first column of A, that's 2, -1, and multiply it by x. Now take the second column of A, -1, 2, and multiply it by y. The matrix equation A times x equals B now becomes x times the vector 2, -1, plus y times the vector -1, 2 equals the vector 0, 3. This is the column view of matrix multiplication, and it reveals that we are really looking for a combination of the columns of A that produces B. This is a linear combination. You multiply each vector by a scalar, then add them together. That's all there is to it. In general, the formula is c₁ times v₁ plus c₂ times v₂, and so on up to cn times vn. This is the single most important operation in all of linear algebra. The column picture puts it front and center. Now here is our specific question. Find scalars x and y so that this combination of column vectors hits the target B. And that is x times the vector 2, -1, plus y times the vector -1, 2 equals the vector 0, 3. Let's draw it. Here's column 1, an arrow from the origin to the point 2, -1. Here's column 2, an arrow from the origin to -1, 2. These are the building blocks. Now we need x equals 1 copy of column 1 and y equals 2 copies of column 2. Start with 1 times column 1. The arrow goes from the origin to 2, -1. Now attach 2 copies of column 2 tip to tail. 1 copy of column 2 is -1, 2. So starting from the tip at 2, -1, we add -1, 2 and arrive at the point 1, 1. Then a second copy of column 2 takes us from 1, 1 to 0, 3. 2 copies of column 2 give us -2 for total. So from the tip at 2, -1, we added -2, 4. 2 plus -2 is 0. -1 plus 4 is 3. The tip lands at 0, 3. Now draw the results. Vector b from the origin to 0, 3. That's the green arrow. The arithmetic confirms it. 1 times the vector 2, -1 plus 2 times the vector, -1, 2 equals the vector 0, 3. Same answer, x equals 1, y equals 2, but a completely different picture. We're not intersecting lines, we're combining arrows. Here's a deeper question. What if b were a different vector, not 0, 3, but something else entirely? Could we still find a combination of these two columns that reaches it? Watch. As we vary the scalars x and y over all possible values, the resulting combinations sweep across the entire plane. Every point in two-dimensional space can be reached. This works because the two column vectors point in genuinely different directions. They are not parallel. Their combinations fill all of R2. But not every matrix is this generous. When the columns line up, when they are dependent, there will be vectors b that you can never reach. That's when the system has no solution. We'll explore that important case soon. 3 pictures, 1 system. First, the row picture. Each equation is a line and the solution is where the lines intersect. This is intuitive in 2 dimensions. Second, the column picture. The solution tells us how to combine column vectors to reach the target vector b. This perspective scales to any dimension. You're always just combining vectors. Third, the matrix form, a times x equals b. This compact notation gives you computational power, same system, same solution, x equals 1, y equals 2. 3 completely different geometric perspectives, all describing the same thing. One thing to notice, a times x equals b literally computes a linear combination of the columns of A weighted by the entries of x. Let me show you what I mean. Suppose A is a 2 by 2 matrix with columns a 1 and a 2, and x is a vector with entries x and y. Then A times x equals x times column 1 of A plus y times column 2 of A, and that equals b. So the matrix form is not just shorthand, it is the column picture written compactly. When you multiply a matrix by a vector, you are combining columns. That connection between notation and geometry is what makes linear algebra so powerful. A times x is a linear combination of the columns of A. Most of linear algebra comes down to one question. Can I combine these columns to reach that target? Linear combination is the operation. The column picture is the geometry, and ax equals b is the language, one equation, 3 ways to see it. That's where linear algebra begins.